So I want to make a quick video on what it means to be a linear transformation and why we might care. Okay, so let's start with something that most people would consider useful in terms of a problem. Let's say I have this nice vector 3, 2, and I want to rotate it by pi over 2 radians counterclockwise. So that's just 90 degrees counterclockwise. So I want the end result vector to be 90 degrees this way. I want to find this vector. Well, let's do it with linear algebra, the way that it tells us it could be done. What we're going to do is we're going to take 3, 2 and break it up into its constituent components almost. Because really, the 3 means I went 3 in the x direction. I can imagine I have 3 copies of 1, 0. So this is 3 copies of 1, 0 down here on the x-axis. And I added 2 copies of 0, 1. That's the vertical component. Okay, so 3, 2 is that plus that. What linear algebra tells us is if I want to rotate 3, 2, really all I have to do is rotate 1, 0, scale it by 3, and then add rotate 0, 1, scaled by 2. I just have to rotate the constituent components. Let's see that play out. What happens if I rotate 3 times 1, 0? Well, 1, 0 is the vector in the x direction. If I rotate that by pi over 2 radians counterclockwise, it's going to point straight up. It's going to become 0, 1. So, like this. So in a way, I can say that 3, 1, 0, it got rotated to 3 copies of 0, 1. If I wanted to find the function that will rotate by pi over 2, well then, it got sent to 3 copies of 0, 1. So I can say that this vector here is 3 copies of 0, 1. And let's do the same thing with 2 times 0, 1 here. What happens to the vertical component? Well, the vector in the y direction gets rotated to this vector, the vector that points in the negative x direction. So this thing gets mapped like this. If I take these two vectors and I rotate them for 90 degrees, it's like that. That's 2 copies of negative 1, 0. So the way to think about it is the x contribution to the vector 3, 2 got sent here, and the vertical component got sent here by this rotation. But look, if I add them up, if I add both rotated vectors, I get precisely the original vector 3, 2 that's rotated by pi over 2. This thing gets sent here. So what this means is to rotate a vector by 90 degrees, all I have to do is rotate its x and y components by 90 degrees and then just add them up. It's like, I could rotate first and then add. Now that is actually what linearity is. So let's write out this algebraically in terms of a nice expression. The rotated 3, 2, this is the function that will rotate by pi over 2. I'm going to apply the 3, 2. What this diagram shows is I can rotate the 1, 0 first and then scale it by 3. And then I can add on the rotated 0, 1 scaled by 2. This diagram is essentially this equation here. And what have I done exactly? I've taken the vector I wanted to rotate it and broken it up into its constituent components and rotated them, and then added the result together. And geometrically, we see that it should be the same thing. This property, roughly speaking, is what we call linearity. And it's one of those inherent properties of rotations, as we can see by the drawing. When you rotate, it's going to have this property because we just drew the vectors and we found out, and of course, it can be generalized, but it's something inherent to rotations. Now, how might this look closer to what's found in your textbook? Okay, 3, 2, I can write it as 3 copies of 1, 0 plus 2 copies of 0, 1. We've established that. And now we see that this is what the textbooks will define to you as being linear. We have the rotated version of a scalar plus a vector plus a scalar times a vector equals, I'm almost just distributing the function into each of the constituent vectors. 3 copies of the rotated 1, 0, that's what this is, plus 2 copies of the rotated 0, 1. That's what this is. And for the purposes of this computation, we can work it out. So just bring the camera down. So 1, 0 rotated by pi over 2 counterclockwise, well, we have established that's going to be 0, 1. Times 2, this should be r. And what's the rotated version of 0, 1? Well, 0, 1 was over here, and then it got rotated. Now it's negative 1, 0. Okay, and what's this going to be equal to? Well, it's going to be equal to minus 2, 3. And if you sort of plot minus 2, 3, you can see it's going to be exactly this vector, which is the rotated version of 3, 2. Because it is, as we can see, 2 in the x direction and 3 in the y direction. So it works out. In the general way this is written out in the textbook, we would have a transformation T is linear if I have a scalar times a vector plus a scalar times some other vector. Notice this is sort of essentially the same thing as this. T in this case is a general transformation. Ours was a rotation. Scalar vector, sort of distributing the transformation into the vector. A T of x plus B T of y. And hopefully you see the resemblance between this definition of linearity and what we have done over here. So what's all this to say is that we have a property called linearity of a transformation T, which occurs when a transformation T satisfies this property for all scalars a, b, and all vectors x, y. And we have seen from this diagram that rotation is a linear transformation. And it means that we can calculate the rotated vector of any sort just by rotating its constituent vectors and just scaling and adding them up.